My name is Bryce Adelstein Lelbach. I'm NVIDIA's architect for HPC programming models. I'm also the chair of the U.S. Committee for Programming Language Standards and the International C++ Committee's Library Evolution Group. Today, I'm going to tell you about the latest developments in the NVIDIA HPC compiler, NVC++ and NVFORTRAN. The NVIDIA HPC compiler is a single interoperable toolchain that supports all major intranode HPC programming paradigms: 4 programming models, Standard Parallelism, OpenACC, OpenMP, and CUDA, 3 programming languages, C++, C and Fortran, and 2 targets, multi-core CPUs and NVIDIA GPUs. It's one compiler that you can use to program your entire system. We believe that parallel programming must be normalized. We want to standardize parallelism, not heterogeneity. Today, serial, CPU-only code is the default. Parallelism is expressed differently for CPUs and GPUs, and big investments in explicit heterogeneity are needed to target GPUs. In the world we envision, parallel code is the default, and most parallelism will be portable across targets. And GPUs can transparently accelerate that parallelism. HPC developers need on-ramps for accelerated computing. On-ramps like Standard Parallelism in C++ and Fortran and OpenACC are high productivity paradigms that let you express parallelism that will get good performance on many targets without being specialized for every single one. They let you get onto the GPU highway with ease. On-ramps don't aim to expose everything or deliver the speed of light performance in every case. The goal is to get all of your code parallelized so that you can focus your efforts on the important things, like the underlying science or optimizing key parts of your code. For those key parts, if needed, you can switch over to a target platform's fast lane like CUDA C++. Both ISO C++ and ISO Fortran have standardized parallel programming facilities, and more are coming in future standards. Standard Parallelism is composable, compact, and elegant. It's intended to be easy to read and maintain. Porting from other parallelism models to Standard Parallelism can simplify your code while also making it more portable. Standard Parallelism can be transparently accelerated by GPUs without any need for explicit heterogeneity. Standard Parallelism is portable. As an ISO standard, it will be available on almost every platform. A number of compilers implement Standard Parallelism today: the NVIDIA HPC compiler, GCC, Intel, and MSVC, to name a few. There are 3 key components to Standard Parallelism in C++ and Fortran. First, there's a corpus of common parallel algorithms. Each vendor can implement these with their own vendor-optimized parallel libraries. Second, there are tools for you to write your own parallel algorithms that can run on any target. And third, there are mechanisms for composing parallel invocations of algorithms into asynchronous task graphs. Let's get started by diving into C++ Standard Parallelism. C++ 17 added parallel versions of the familiar C++ sequence algorithms. The parallel version of an algorithm has an additional execution policy parameter, which describes what class of parallelism is allowed. The execution policy requests parallelism, but does not require it. The implementation may choose to not vectorize or parallelize a particular invocation of an algorithm. The standard doesn't specify what type of parallelism may be used, except that it must fulfill the forward progress guarantees of the execution policy. Fibers, thread pools, and GPUs are all acceptable implementation options. Last year, NVC++ 20.7 introduced GPU-accelerated C++ standard parallel algorithms. NVC++ 21.3 introduces support for running C++ standard parallel algorithms on multi-core CPUs. With standard parallelism and NVC++, you can switch between targeting a CPU and a GPU with a single command line option. In an upcoming release, we'll add support for fat binaries, executables that can run on different GPU architectures. We're also developing support for transparently targeting multiple GPUs from a single process with C++ standard parallelism. If you want to learn more about C++ standard parallelism, check out our blog post on it. LULESH is a mini-app for Lagrangian explicit shock hydrodynamics on an unstructured grid. It's designed to stress vectorization, parallel overheads, and on-node parallelism. It's about 9,000 lines of C++. It has parallel versions for a number of different programming models, including standard C++. As you can see, we were able to run the same code in parallel on CPU and GPU and get good performance on both. STLBM is a framework for parallel lattice Boltzmann simulations on multiple targets, including multi-core CPUs and GPUs. It's implemented with C++ standard parallel algorithms. It doesn't use any language extensions, external libraries, vendor-specific code annotations, or pre-compilation steps. It's developed by Jonas Ladd at the University of Geneva. To learn more, check out his talk at GTC this year. Parallel sequence algorithms are just the start of C++ standard parallelism. A lot more is coming down the road. Views, first introduced in C++ 20, enable iteration over multidimensional indices, composition of algorithms, and kernel fusion. Views can be used with the traditional iterator-based C++ algorithms, but views work more naturally with the new C++ 20 ranged-based versions of these algorithms, so we plan to introduce parallel versions of these as well. We will also expand beyond 1D sequence algorithms. The committee is working on introducing C++ linear algebra algorithms and array types that abstract the BLAs. Under the hood, these interfaces would connect to accelerated vendor libraries like cuBLAS and cuTensor and utilize hardware like NVIDIA Tensor Cores. Standard C++ will also introduce executors, an abstraction for expressing and managing asynchronous execution. Executors will give you a mechanism to write your own kernels and compose parallel task graphs that can run anywhere. Now let's move on to Fortran standard parallelism. Fortran 2008 introduced do concurrent, a form of the do loop which the compiler is allowed to parallelize. Like with C++, do concurrent is just a hint to the compiler. The compiler is not required to vectorize or parallelize a do concurrent loop, and the standard doesn't prescribe a particular type of parallelism to be used. This implementation freedom makes do concurrent portable to almost any target. NVFORTRAN 20.11 introduces do concurrent for both CPUs and GPUs. If you want to learn more, check out the blog post we wrote about it. You can add locality specifiers to a do concurrent loop that control how variable names referenced inside the loop are treated. Locality specifiers only affect variable names, not subscripts or components. Every thread has its own instance of all variables listed as local. Those instances will be undefined at the start of every loop iteration. Local init is like local, but each instance is set at the start of every loop iteration to the value of the variable from before the loop. Every thread uses the same instance of variables listed as shared. Default none indicates that all variables used in the loop must be explicitly listed in one of the above specifiers. Otherwise, a compilation error will occur. There's a new locality specifier planned for Fortran 22X that will also be coming to NVFORTRAN soon, reduce. Reduce tells the compiler that the loop is a reduction of a certain operation on a certain variable. The operations listed here are supported. We wrote a simple Jacobi mini app with do concurrent. By changing just one command line switch, we were able to run the same code in parallel on a CPU and a GPU and get good performance on both targets. We've started exploring the use of do concurrent in NWChem, one of the major computational chemistry frameworks. These are results from porting a benchmark for one of NWChem's key kernels, CCSD, from the tensor contraction engine module. Again, the same version of the code runs in parallel on the CPU and the GPU. All you have to change is one command line option. Just as we accelerate standard algorithms in C++, as of 20.11, NVFORTRAN can accelerate a wide variety of Fortran array intrinsics and patterns. On the left, we have a naive matrix multiplication written with raw do loops in OpenACC. If we replace it with a standard matmul call and use NVFORTRAN's stdpar mode, it'll be GPU accelerated using cuTensor and NVIDIA tensor cores under the hood. Not only is the code simpler and cleaner, it's also a lot faster. There's many different standard Fortran array intrinsics and patterns that we can automatically GPU accelerate. If you want to learn more, we wrote a whole blog post on it. Next, let's talk about OpenMP. The NVIDIA HPC compiler has supported OpenMP for CPU parallelism for a while. But now, in the 21.3 release, we're introducing support for a subset of the OpenMP target facility for NVIDIA GPUs. If you want to learn more, there's another great talk at GTC this year with all the details. Finally, let's talk about CPUs. We've always supported x86, 64, and Power CPUs, but when we launched the NVIDIA HPC SDK last year, we also launched support for ARM. The NVIDIA HPC compiler is ready for ARM. Our auto-vectorizer has been tuned for ARM, and we have support for all of the ARM vector intrinsics. Our host parallelism offerings, C++ Standard Parallelism, OpenACC, and OpenMP, all support parallelism on multi-core ARM systems. We've also got support for all three of our floating point models, precise, fast, and relaxed, on ARM targets. There's another talk at GTC this year about bringing HPC apps to heterogeneous ARM targets if you want to learn more. So that's our story. Write code in standard C++ and Fortran, and it can run on your CPU, GPU, or any other target. That'll be good enough for most, maybe even all of your code. With standard parallelism, you can minimize the places where you need to write specialized code for different target platforms. And with that, I think we're done. Actually, hang on a minute. There's a problem with what I just told you. So, I just told you a story that was fundamentally rooted in incrementalism. Use standard parallelism in most places and use CUDA C++ only where it's needed. But today, while NVC++ has standard parallelism, OpenACC, OpenMP, and CUDA Fortran, it doesn't have support for CUDA C++. And conversely, while NVCC has CUDA C++, it doesn't have support for standard parallelism, OpenACC, OpenMP, or Fortran anything. Today, there's no option for an incremental approach in C++. You either use standard parallelism exclusively, you use CUDA C++ exclusively, or you have to use two compilers in conjunction, which is, probably going to be unpleasant. I promised you one compiler for your entire system, which supports 4 programming models. But that story's not complete today. There's one piece that's missing. That's why today I'm pleased to announce that CUDA C++ is coming to NVC++. That's right, NVIDIA will have a second CUDA C++ compiler. In NVC++, you'll be able to use all of our programming models and seamlessly switch between them. And all 4 programming models are interoperable. They can be used within the same source file. They're ABI compatible with each other and NVCC. You can do NVC++-stdpar-CUDA-ACC-MP and use a CUDA kernel and an OpenMP loop and an OpenACC loop and call a C++ parallel algorithm, all within the same translation unit, and that just works. This is, we believe, a huge ecosystem enabler. We'll have a compiler, a single interoperable stack that supports all the major intra-node HPC programming models. Users will be able to combine components and libraries developed by different teams using different programming models. NVC++ CUDA is about so much more than just programming model interoperability. Let's talk about heterogeneous compilation models. NVCC uses a split compilation model where an external host compiler is paired with a device compiler. NVCC splits code into target-specific variants during preprocessing before compilation even begins. The code is independently preprocessed, parsed, analyzed, and optimized n times, one for each different target. While NVCC has control over the device compilation, host compilation is controlled by the host compiler that NVCC is paired with. NVCC must work within the parameters and constraints of what that host compiler supports. Unlike NVCC, NVC++ uses a unified heterogeneous compilation model. There's no separate host compiler and device compiler. There's just one compiler, NVC++, a unified stack that orchestrates everything. In the unified model, we preprocess once, we parse once, we build one unified abstract syntax tree, we build one unified intermediate representation, we analyze it once, and we perform high-level optimizations on it once, and only then do we split into code gen for specific targets. Why does unified compilation matter? Well, it's more efficient. You parse, semantic analyze, and optimize once instead of n times. You have a single canonical representation of code. That means that you've got greater visibility, greater potential for analysis, greater interoperability, and greater control both within and across host and device code. This means that you have greater robustness, you have better diagnostics, you can have better language support. NVC++ already has full support for C++03 through C++17 and partial support for C++20 in all programming models, including CUDA C++. We expect to have full C++20 language and library support in 2022. In fact, I think NVC++ will probably be one of the first compilers to fully support C++20. Unified compilation also lets us build exciting heterogeneous programming features that we can't deliver in a split compiler like NVCC. Now, let me be very clear, we're not trying to build a better NVCC. NVC++ is fundamentally a different compiler with a different compilation model. There's a trade-off between these two different models. Split compilation can't support everything that unified compilation can, and vice versa. Each has different strengths. 100% feature compatibility with NVCC is an explicit non-goal for NVC++. Now, let's dive into some of these unique heterogeneous features in NVC++. In CUDA C++ today, heterogeneous functions are opt-in. You explicitly annotate which functions should be compiled heterogeneously. But we want code to be parallel by default, to be heterogeneous by default. And that's why we're introducing execution space inference for CUDA C++ in NVC++. The idea of execution space inference is simple. The compiler determines what targets a function should be compiled for based on usage. When a function is used from a particular target, if its definition is reachable, we attempt to compile it for that target. This isn't a new idea. We've used execution space inference in Standard Parallelism, in OpenACC, and in OpenMP. It's a huge ecosystem enabler because it makes it substantially easier to port code to CUDA C++. I have a feeling that many of you have spent some chunk of time taking code and doing nothing more than adding host device annotations everywhere to it to get it ported to CUDA C++. And I'm very glad that I can tell you today that you don't have to do that anymore. You don't have to sprinkle host and device everywhere. The compiler can just figure it out for you. As I said, inference occurs on use. All functions have an execution space that describes what targets they need to be compiled for. Functions without annotations have an open execution space, which starts out with a default set of targets. Today, that's just host. Inference may add other targets to the execution space of such functions. Note that this is a divergence in behavior from NVCC. NVCC assumes that all unannotated functions are host only. NVC++ doesn't. If you want a function to be host only, you'll need to explicitly annotate it. Functions with annotations instead have a closed execution space, which can never be added to. In the case of G, its execution space is just host and will never be expanded. Kernel functions also have a closed execution space of just device. Functions that are declared in a source file but defined in a different source file have a closed execution space as well. If they are unannotated, it's the default execution space. If the declaration has annotations, those are used instead. When a function is called, the compiler checks if the called function's execution space contains all of the targets in the calling function's execution space. If it does not, the missing targets from the caller are appended to the called function's execution space. In this example, I calls H. I has device as a target, but H doesn't. So device is added to H's execution space. This process is recursive. H, which now has an execution space of host and device, calls G and thus propagates device to G. F, which is not called by anyone that we can see, doesn't have device added to its execution space. If a function has a closed execution space, it is an error to call it from an execution space that it does not support. For example, if G has host-only annotations, it will have a closed execution space of just host. We'll get a compilation error when H, which has device in its execution space, tries to call G. If a function is defined in another source file, you may need to use annotations on declarations to ensure the compiler knows what targets the function supports. For example, if G is compiled in another source file for both host and device, but it's not annotated as such in the declaration that this source file sees, we'll get a compilation error. If we add host device annotations to the declaration of G, then the compiler will know that G supports device targets, and everything will work fine. Today, in CUDA C++, you can't use the C++ standard library in device code. It's provided by your host compiler and not designed to support GPUs. 2 years ago, we launched libq++ for NVCC, an opt-in incremental solution to this problem, which provides a high-priority subset of the C++ standard library in the CUDA: stud namespace. With NVC++, there is no host compiler. There is no conflicting host C++ standard library. We provide the entire toolchain, and soon that will include a full C++ standard library for your entire system, including your GPU. Stud, not CUDA stud. Everything will work in host code, and most things will work in device code. It'll be available in all of the programming models that NVC++ supports. If you want to learn more, you should listen to my GTC talk on the NVIDIA C++ standard library. In CUDA C++ today, we have a way of making objects accessible to both host and device code, unified memory. Unified memory is opt-in. You have to explicitly choose to make an object accessible heterogeneously. Automatic unified memory flips the default. All dynamic memory is unified memory unless you explicitly opt out. Today, it doesn't support global variables, stack variables, or dynamic memory from source files that were compiled with automatic unified memory off. This feature has been available in Standard Parallelism, OpenACC, and OpenMP for a while, but now we're bringing it to CUDA with NVC++. We've talked about a bunch of new features that come with NVC++ CUDA. Now let's talk about the one major feature of NVCC that we cannot support, CUDA Arch. CUDA Arch is a preprocessor-based facility for specializing code for different targets. It's a macro which NVCC gives a different value when it preprocesses the source for each target. For example, it allows you to write a terminate host device function that uses inline ptex assembly when called on device and an OS call when called on the host. We can never support CUDA Arch in NVC++. NVC++ builds a single, unified, and heterogeneous representation for all targets. We preprocess once, we parse once, we build one unified abstract syntax tree, we build one unified intermediate representation, we analyze it once, and we perform high-level optimizations on it once, and only then do we split the code into variants for each different target architecture. This unified representation is essential to our compilation model. Without it, we cannot offer many of our key features, and CUDA Arch fundamentally compromises that model. Imagine you have a struct that has different members on different targets. What is the size of that struct? How do you model that struct in a single unified AST and intermediate representation? What happens when you pass one of those structs between host and device code? What happens when you have functions that return different types for different architectures? How do you model that in a single unified representation? What about a template instantiation or a variable with a different type on different architectures? How do we model this in C++? The short answer is we can't, at least not in standard C++. CUDA Arch allows you to write code that fundamentally violates standard C++'s compilation model and the one definition rule. And in a compiler like NVC++, where we have a single canonical and unified representation, we simply can't support something like CUDA Arch. So we're introducing a modern alternative to CUDA Arch, IFTarget, which both NVCC and NVC++ can support. While CUDA Arch is preprocessor based, IfTarget is a language construct that we can model in our AST and intermediate representation. By construction, IfTarget prevents you from writing many of the subtle bugs that CUDA Arch enables. An IfTarget statement is a special type of selection statement which takes a target description as an operand. If the current target matches the description, the true statement is taken, and the false statement is eliminated. Otherwise, the true statement is eliminated, and the false statement is taken. If a statement is eliminated for a particular target, then it does not need to be valid for that target. For example, a statement eliminated for hosts can use shared variables or inline ptex assembly. A statement eliminated for devices can make OS calls or use SIMD intrinsics. There is no runtime cost to an IfTarget statement. It's always evaluated at compile time. However, it cannot be used in a context per context because that would allow target variants to leak into the type system. Target descriptions are constructed using the following primitives from the new NVTarget header. Traditional logical operators can be used to compose target descriptions together. IsHost will match any host target. Likewise, IsDevice will match any device target. Provides matches any target compatible with S, where S is some capability. For example, SM70 or SM80. IsExactly matches only targets that are exactly S. Here are some examples of porting from CUDA Arch to IfTarget. In many cases, the switch is very straightforward. However, if CUDA Arch is being used to cause types, template instantiations, or context per evaluations to differ across targets, then structural code change may be required. With IfTarget, all target variants must remain encapsulated within a function. It cannot leak into the type system by construction. IfTarget can only be used within a function scope. IfTarget can't make a function return a different type on different targets. IfTarget is guaranteed to be evaluated at compile time, but can't be used in context per contexts. IfTarget's operands must be context per and cannot depend on a template parameter. That's it for CUDA C++ for NVC++. It'll be coming to the NVIDIA HPC SDK soon. The NVIDIA HPC compiler, 4 programming models, 3 programming languages, 2 targets, 1 compiler for your entire system. You can get it today by installing an NVIDIA HPC SDK package or container. If you want to learn more about the latest developments in NVIDIA's HPC software stack, check out these talks, panels, and blog posts. I hope you all enjoyed this talk. If you thought this was exciting, tune in for my talk at GTC 2022, because we've got even bigger things coming down the road.